All right, we're going to get a little bit more specific with our Riemann sums, and we are going to use rectangles of fixed width. And when you do that and you set each subinterval so that it has the same width, it's called the rectangular approximation method, or RAM for short. LRAM is going to use the left endpoint of every subinterval, RRAM uses the right endpoint, and MRAM is going to use the midpoint of the subintervals. So we're just going to dive right into this, and we are going to use the first example is the integrand is 1 over x, so that's the actual function we want to find the definite integral for. It's telling us that we've got an interval from 1 until 9. Those are the bounds of the integral. Okay, so I'm just going to do a quick little graph. The graph of 1 over x looks something like this. And we're specifically looking at the x values from 1 until 9. So we'd be looking for this little area right here between the curve and the x-axis. So that's what we're trying to estimate or approximate using this RAM method. The first one is going to ask us to find an estimate using the left endpoint, so LRAM. And since all of these subintervals are fixed width, you can determine how wide each subinterval is going to be based off of what approximation, how many intervals you're going to use. So if you look up here where it says LRAM 4, that's telling you how many subintervals you need. If you take 9 minus 1 and divide it by the number of subintervals, which is going to be 4, so you're trying to cover a width of an x range of 8 using 4 subintervals. That's going to give you a width of 2. So that's where that comes from. So since all of them have the exact same width, you can basically factor out the width. Okay, so instead of doing 2 times the first y value plus 2 times the second y value plus 2 times the third, etc., you can just factor it out because they're all fixed width. And since the subintervals have a width of 2, this is going to give you 1, 3, 5, 7, and 9. So if you're looking at LRAM, you're going to use the left endpoints of each subinterval. So the first subinterval from 1 to 3, the left endpoint would be 1. So we're going to use f of 1 for the first height. The second subinterval goes from 3 until 5, so the left endpoint of that guy would be 3. The third subinterval, we would use the left endpoint of f of 5. And the fourth subinterval, the left x endpoint is 7, so we'll use f of 7 for the height of the rectangle. So this is going to give us 2, and then again the function values come from plugging the number into the integrand. F of x again was equal to 1 over x. So just plug in each of those values to get the y value. This is going to give you 1 over 1 plus 1/3 plus 1/4. I said fourth, I meant fifth, plus 1/5 plus 1/7. Okay, you can do all that on your calculator, and this will give you an approximation, 3 decimal places always in this class, 3.352. Okay, now even though I haven't shown you how to do RRAM specifically and MRAM specifically, I bet you can figure it out. Go ahead and hit pause and see if you can determine which x coordinates you're going to be using in order to come up with the height of the rectangles in each subinterval, and then come on back. All right, let's see how you did. For RRAM, using 4 subintervals, you're just going to use, again, the width is 2, and this time you're going to use the x coordinates of 3, 5, 7, and 9. So the height of the rectangles is determined by f of 3, f of 5, f of 7, and f of 9. Okay, so if you plug that in, you're going to get 1.575. And then for MRAM, Now this one you're not using any of the points that you actually see on the graph. You're using the midpoints at the subintervals. The width of each subinterval is still 2, but this time you're going to use f of 2. That's the midpoint of the first subinterval. F of 4, f of 6, and f of 8. And you plug all that in and you get 2.083. Okay. I ask you which one appears to be the most accurate. You know, if you draw in LRAM, pretend that goes on the 1 here. That created the height using f of 1. Then you use f of 3, f of 7, and f of 5. Pardon me. So that's using the left endpoints. So you can see that the rectangles are actually above the curve. Then I'm going to switch colors over to, let's say, orange, and I'll do RRAM. So if I go starting at 3 and I use that for my height and I go over and down, then I used 5, go over and down, 7 over and down, and 9 over and down. Those are all underestimates. Let me switch colors one more time. And you don't need to sketch all this out, but this is just for discussion purposes. Now we're going to use a height of at x equals 2. So that would be the height of MRAM. And this would be the height, oops, go on to the curve at f of 4. Here's f of 6 and f of 8. For each of those, the green ones, there's a little bit that's under the curve and there's a little bit that's over the curve. So as far as, being the most accurate approximation, MRAM is almost always going to do it for you. It's just it's got a little bit above and a little bit below. So there you go. Okay, this is the portion of the notes where I'm just going to do a couple of practice problems. So actually I'm gonna write down a couple of problems, then I'm going to give you a chance to do them on your own, and then you can come back and check your answers. So we're going to start off with the first problem. We'll have you do estimate a definite integral from 0 to 6 of x squared and we'll use 2 subintervals. And I'll have you do LRAM, and I'll have you do MRAM. And then for the second one, same directions, we'll have you estimate. And this time we'll do the integral, the definite integral from 0 to 4. And we'll have our integrand be x squared plus 1. And this time I'll have you do RRAM. And let's just go ahead and use, do you want to use 2 or 4? Well, let's just use 2 again. And this time do MRAM 2. Okay. And then I'll give you one more after this, but go ahead and give those a shot, and then I'll show you the answers and how we did the work. Alright, for your first one, you were integrating from 0 to 6 of x squared dx, and I had you first do LRAM of 2. So the first thing is to figure out how wide your subintervals are, and if you do the 6 minus 0 divided by the number of subintervals, you're going to get a width of 3. So for LRAM, you're going to use the left endpoints of each of the subintervals. So the first subinterval goes from 0 to 3. So you're going to say LRAM 2 is equal to the width, and you're going to use f of 0, and you're going to use f of 3. Okay, if you want to think about a number line, right, here's the x number line. Oops. There we go. So here's your x number line from 0 to 6, and if you've got a width of 3, here's your first subinterval from 0 to 3, and your second one is from 3 to 6. So that's why we're using f of 0 and f of 3. Okay, and again, for each of those, you can just plug in your function. You're going to have 0 here, and you're going to have a 9 here. So overall, you should have a value of 27. This is the approximation of the integral from 0 to 6 of x squared dx. So it's just one approximation. Okay, so that's LRAM. And then if you wanted to use MRAM, using the same width of 3, you're going to have 3 times f. Now, the midpoint of the first subinterval is going to be 1.5. And the midpoint of the next interval is going to be 4.5. That's going to give you a value of 67.5. So very different answer than we got for LRAM. And I want you to think about why we got such a different answer if you think about the graph of x squared and what that looks like. We're going to go ahead and do the second example answer and see how you did on that one. Okay, so this was the second example. The integrand is x squared plus 1, and you are going from 0 to 4, and I'm asking for an approximation using the right-hand approximation with 2 subintervals. So again, the first thing is to determine the width of each subinterval. You're going to go from 0 to 4, so that's 4 minus 0, all divided by 2 subintervals. So the width this time is going to be 2. Okay, so again, if you're a visual person, draw out a number line. It's not silly, it's going to help you out. So width of 2 would go here. Okay, so that means for the right rectangular approximation method, you're using the right endpoints. So you're going to have the width of 2, and this time you're going to use f of 2 and f of 4, the two right hand. Alright, so choose, my cat is meowing, crazy kitty. Alright, and then f of 4 squared 16, plus 1 is 17. So this is going to give you a value of 44. And for MRAM, using 2 subintervals, still a width of 2, but this time you're going to use f of 1 and f of 3. Midpoints. And we're getting 24 for this one. Okay, so that is the rectangular approximation method with fixed widths. And we are going to do one more example, and this one's a little bit different. So if you're still watching the video, good for you. You're going to have an edge up on the competition. We're actually going to take a look at what happens if the data given to you is actually in a chart instead of an equation. All right, this is going to be the last example that I'm doing. I'll give you a second to kind of write this down, or you can hit pause. But we are going to use data in a table this time and not an equation for our function, or not an integrand that we are given. We are going to estimate the distance that's traveled of a particle or an object from t equals 0 to t equals 6, and we're going to use a left approximation. The first thing to point out is that the intervals are not the same width. Okay, so if you were to think about this, if we were to graph this time on the x-axis and velocity in meters per second, and this was seconds. Okay, the first thing to point out is we're going from 0 to 2, and then from 2 to 3, 3 to 5, and 5 to 6. So this is not at all an equal width. So we're going to have to do each individual rectangle separately. But again, we're going to use the left endpoint. So for this first subinterval, we've got a width of 2, and we would be using our function value of 0. Our next subinterval is from 2 to 3, and that's a width of 1. And we would use f of 2. Our next subinterval is from 3 until 5, so that has a width of 2, and we would use f of 3. Our fourth subinterval is from 5 until 6, and that's got a width of 1. and we'd use f of 5. Okay, so you would say that the distance from t equals 0 to t equals 6 is approximately this. Now, we don't have a function to plug into, but you are just going to take directly from the table. We'll call this our f of x here, and we'll call this our x. Okay, so f of 0 is 3, and 1 times f of 2 is 4. 2 times f of 3, which is going to be 7, and 1 times f of 5, which is 8. So we're getting about 32, and the question is, what do you get for units? Well, when you multiply meters per second, which was all of the function values, times any of your widths, which is in seconds, you're going to get a value of meters. Okay, so this is how you would use data to approximate, and if you followed along and you wrote this down, this is going to help you out a lot, so good for you, and I'll see you guys in class.